Assalamu alaikum. So we are at NCP. Today is our third day on 13 summer school at LHC Physics. So very interesting lectures today. And मैं आज पूछना चाहूँगा, ये हमारे साथ दो भाई हैं, तैयब भाई हमारे सीनियर फिजिसिस्ट हमारे फ्यूचर में, और ये हमारे सजाद भाई, ये भी फ्यूचर के फिजिसिस्ट बनेंगे इंशाल्लाह. तो आज हम इनसे एक्सपीरियंस पूछते हैं कि इनको कैसा लगा. हाँ जी सजाद भाई, क्या एक्सपीरियंस है एनसीपी में?
एक्सपीरियंस तो बहुत ही अच्छा है, क्योंकि हम 2-3 दिन से यहाँ पे मुख्तलिफ सेशंस अटेंड कर रहे हैं, उसके साथ साथ लैब में मुख्तलिफ काम कर रहे हैं सिमुलेशन पे. तो बहुत ही सही एक्सपीरियंस है यार, और बहुत अच्छा जा रहा है.
एग्जैक्टली
करते हैं कि और भी जो इनकमिंग 2 डेज हैं वो भी अच्छे हो जाए.
जी इंशाल्लाह होप यही है, बिकॉज यहाँ पे हैंड्स ऑन एक्सपीरियंस है, काफ़ी अच्छा माहौल है, तो बहुत कुछ सीखने को मिल रहा है. तो बहुत शुक्रिया हमारे साथ भी.
Running faster and faster. I don't know what we're after, yeah. We keep up with disaster. I'm thinking that they're after me. We're running like faster and faster. We're running like faster and faster.
They're completely loud, but we have never seen it before. This is the earlier mentioned C discovery at LHCb, and there's an animation that I hope will work. So this is how we take the data. And the thing I want you to look at this and ask yourself, at which point are you convinced that there's really a peak here? That it's real, it's not some fake fluctuation. And one important aspect of statistics and the interpretation of data is to quantify that sort of gut feeling and make it quantifiable in terms of probabilities and numbers. So how likely, assuming there's no psi double C, how likely it is that I see a peak like this just as a statistical fluctuation? And I would say very unlikely at the end, but quite likely still. I wouldn't see anything there. And at some point you say, oh, that's probably real. So we want to quantify this. We want to be scientific about it, not just have a gut. So, yes. The problem, I mean, there are many of these false discoveries, although we're getting, I think, much better with statistics, and I have the impression there are a few of those in the future. But the problem is that nature doesn't allow us a direct view of the fundamental parameters of our model. If you ever had an undergraduate experiment measuring, say, the gravitational constant G or something like this, you will never get the exact value. Actually, we don't know the exact value because there are always some uncertainties in these measurements. They might come because a truck goes past your high precision, low vibration setup, or the electricity supply fluctuates a bit, all sorts of things. So if you say that we measure that the Lagrangian of the standard model is this kind of thing, that's the thing that John Ellis will talk about, I suspect. What an experiment like CMS gives us is at best this. Probably only a little section of this, because they're actually getting only the low energy part of it, so it's what we hear. But yes, so and statistics is a way of interpreting a picture like this and say, not only, it's not that we can take the blur away necessarily, sometimes we can. More often, it's important just to understand how little or how much we know. What can we say with confidence? What aspects of the standard model do we know? Or the measurements that we take, and what do we not? That's fine. So you'll see how we.
Why don't you respond? Come on. उनके पास है वो तो कर सकते हैं, लेकिन respond. But those all who have, let's say, new phone or the jazz, they can respond right away rather than just waiting for you to.
Sorry about that. Does anybody know which band that is? No? Well, shows my age. That was sort of quite in vogue when I went to the UK first in 1996 or something, a bit later, before you were born. So, okay, you don't know what that is? I quite like it. It's called Blur. And that is the topic that I want to introduce. It is the blur that I mentioned earlier. This is nature. This is our picture of it. And that blur tends to be Gaussian. And the big question is, why is that the case? Why is the blur that we get, why is that Gaussian? And that is, well, this is a Gaussian. This is a Gaussian distribution. So a Gaussian distribution has a mean, and it has a standard deviation, and the standard deviation goes from here to here, and famously, so this area covers about 68%. That's how Gaussian looks like. You will probably have seen it, maybe you call it bell curve or something like that. This was me with Gauss in Göttingen. Göttingen is a friend of mine lived there, and there he lies, and he has, you can see he has a magnificent sideburns. And this is Gauss again, this is sideburns. And on money that doesn't exist anymore, that was pre-Euro, but it was considered important enough that this curve and the formula for it actually was on the money in Germany. So, and the Gaussian is important because of the central limit theorem, and this is the central limit theorem. So, take a random variable y, and that random variable is a sum of some other random variables that are called x with an index. So each of these x is a random variable, and they're independent of each other. That's an important part of this. And each of these x has a mean. These means are generally different, and it also has a standard deviation and a variance, which is the square of the standard deviation. Then, that is the, and then that also explains why mean and standard deviation are so good. Y has, I call it expectation value. I often use expectation value instead of mean for theoretical distributions. Same thing, so mean that is the sum of the means of the other variables. It has a variance that is the sum of the variance of the other variables. Important, so the variances add up. Importantly, this means that the standard deviations do not add up, right? The standard deviations add up. It's the variance that add up, and then if you want to use a new standard deviation, you have to take the square root of these, the sum of the variances. And then the most magical thing is whatever the distributions of these x parameters, and it really doesn't matter, I will prove that to you, well, in a very experimental physicist way, the distribution of y becomes Gaussian as we get more and more random variables that we add up. And that's why this is so important, for example, when it comes to estimating errors. Errors or uncertainties of your measurement, they come from all sorts of sources, but usually many of them. I mean, there's a truck going past your lab, there's phone mass and interferes with your electricity, there's some thermal fluctuation, there are many different independent causes. Each of them causes the measured value to fluctuate around the true one in a different way, and we have no idea in what way. But with this, we know that the result of that is most likely a Gaussian, as long as you have enough of those different variables, and that's the magic of this. So out of basically complete ignorance, we don't know the individual distributions, we actually get something that we can understand. This is quite a magic thing. That's why the central limit theorem is amazing. So, what I plan to do, and that I will still do, although we will not do this is why at the end of this lecture we introduce this new problem, I will ask you to roll dice. These are my dice. You will each get dice. You'll roll these dice, and submit results. And I will ask you to roll a die once, submit the result. To roll a die twice, or 2 dice, submit the sum. And then to roll 10 dice and submit the sum of that. That's your task. And there will be a prize for the largest number of entries. So I hope you use it several times, because we said this works for n going to infinity. Although there are many of you, you're not infinite. So do it many times and let's see how this looks like. So, well, actually, this is the wrong end. I'm being unfair. Yes, no, actually, this is what I want. So the largest number of entries wins. There's a second one where you can guess or predict the result. And if you look at the definition of the central limit theorem, you should be able to tell me the result of what the mean and the standard deviation of each of these distributions is. Well, for the first distribution, you will need to calculate the standard deviation of the result of rolling a single die. That might require a little bit of thinking. I might help you with that. And then for the others, it follows from the central limit theorem. So these are the 2 things I want you to do, and we will need them, especially this one, we will need for the first lecture next week that I'll give. So I really need you to go somewhere where you have decent internet access, roll some dice, and submit the results. You look at me as if it was a scary task. It's easy. Might be all you do. I'll tell you how to do it. This is how the interface will look like to scare you less. I can just open link. That's where it is. Name. My name is Jonas. And then I'll roll the die. I got a 2. You see how it works? Right? I rolled 2 dice. I got 4 and 4, which is 8. And then I rolled 10 dice. Oh well. 1, 2, 3, 4, 5, 8, 10. And that's of course a bit harder, but I think you can do it. This is 7, 17, 27, 37. That's 37. And I submit this. And the result has been recorded. That's great. And then I can have a look at the responses. Oh, some people have already, very good. I see that I'm not the only one. Ikra, you're a star. Whoever's Ikra, are you here? You're a star, Ikra. Fantastic. So we have Ikra in the lead. The large number of submissions will win. And we'll look at the score sheet when we start the next lecture. And then we will look at, of course, at how the distribution will look like. So I shall see you next week. Thank you very much.
Questions or comments?
And this has been really a big success. So that now in spouting on also as almost as good as offline particle flow objects available. And yeah, this is just sort of making the point again that I was making verbally to some extent. So the tracking is really one of the challenging things, because it already takes a lot of time in the reconstruction, and then also the time grows very quickly with an increased instantaneous velocity, especially for higher. And most of the time is spent during pattern recognition, the building of first tracks, and then one really has to continuously work on improving this to avoid that the scaling is so badly so bad. So then if there's one can here see a comparison between how it would have stayed if one just would have done what was done in run 1 and run 2, and there one can see that, okay, for the higher and instantaneous luminosities we're dealing with during run 2, that we will not have worked. But then there's still many optimizations. Also the key, and then this uploading to GPUs also has. And the second sort of big ingredient for getting first the particle flow objects and then later the jets and the missing transverse momentum is the calorimetry. And there, this is a sort of destructive method, so we want to measure the total energy of the particle, but then depending on the exact implementation of the calorimetry and also the granularity, then there can also be additional pieces of information that can also help with linking more easily to the tracks and getting an overall picture. So the future high granular calorimeter, for example, is so finely grained that one can actually do some kind of tracking also within the calorimeter. But then also there's a good time resolution and the particle shapes are not too long, then one can also avoid contamination of the signal from out of time perhaps. So that's something that I think I briefly touched upon also, but just as an illustration here, there's some sort of older by now pictures of the pulse shapes, where you can see that we have this 25 nanosecond bunch spacing, so every 25 nanoseconds, so there can be new collisions that leave some signal, but then these pulse shapes and the E plan and the H plan are much longer than these 25 nanoseconds. So here, each of these numbers is a 25 nanosecond time slice, and that then means that one also has to take care of the energy deposits of previous and following bunch crossings, and then what is generally done there is fit of these pulse shapes from previous and following bunch crossings to then filter out what has been the energy deposition in the actual event of interest. But for that, of course, everyone also needs to do this sampling in time slices to then be able to tell apart that, okay, we have integrated all the energy deposits over a very long time. That means we split the split and such that we can do this. General properties of sort of signal left in the calorimeters, and also the way things are done and the way things are also different with respect to the tracking. The length of the showers, as this is a destructive method, and we are creating new particles in these showers. It does increase the length of the showers with the energy, but it doesn't increase linearly at least. So that's some sort of logarithmic increase with the energy of the length of the showers, but then the hadronic showers are much more irregular than the electromagnetic showers. With each sort of generation of pair conversion followed by radiation, the energy then halves, and then the shower starts to be absorbed if the energy of the constituent particles falls below this critical limit, and then one can sort of quite easily then know how many photons of what energy will be there in the end, and that then sort of correlates nicely with the with the energy of the incident particles. But then the hadronic showers, they are really mixed. So they have this electromagnetic shower component increasing momentum or energy also, and then the sort of real hadronic path, which then eventually also always produces some electromagnetic shower path. These products of strong interaction will then start these mixed showers. One needs more containment, and the shower shape fluctuates much more, and also then depends on the incident particle and its energy. Here you can see, just to illustrate how this electromagnetic energy fraction is increasing, that then for higher energy incident particles, this electromagnetic energy fraction is much higher, but also fluctuating. So it really depends on at what point how much of the energy goes into the electromagnetic part, and there's a huge spread. So that is one of the problems there. So calorimetry in a nutshell, particle interaction with matter is what is the sort of main starting point, and ingredient we want to absorb and destroy the particles, and then see what comes out and use that information to then get some signal. So this the interaction that happens then depends on the incoming particle, in particular whether it's an electron or photon, which then exclusively has this sort of nice and clean shower, or whether it's some hadron, which then will start this more complex kind of shower. And the energy loss is then transferred to the signal, which very often is light, but doesn't have to be, also directly charges. And then one needs to collect the signals, convert them into some electric signal, and amplify it, digitize it, and then do something with it. What is nice with the parameters in particular, those that are sort of too expensive to build, let's say, the second one can cover also as much solid angle as possible. So if one wants to have full coverage, for example, for this missing transverse momentum, and that is a very important way how to achieve that, how to capture everything. So just about the CMS speaker, if you were, I was already mentioning these crystals here. There are some pictures of them, how they looked, at least when they were still fresh. So by now that's actually also for operation quite advantage. They have darkened a lot, so one needs to amplify the signal by a very large amount. The fraction on the percent level also of the transparency is still there. Also, since a few years, one has a longitudinal separation of the readout. In the past, it was just everything in the whole tower was read out at once, but now in principle, one can also play around with the shower shapes. So the first layers are lumped together, and then there's, I think, sort of it's separated into 4 depth layers, something like that. Then the end cap is kind of similar. The outer detector is beyond the superconducting magnet. That's a bit of the tail catcher of these showers, which then has to do with the fact that the radiation lengths or the interaction lengths of the calorimeters are not that long, and then we have this quite radiation different technology, hadron forward calorimeter, which then has these fibers and covers them more forward. For the LHC, I was mentioning as the thing that will come around for the run 4, so the next next data taking period after the upcoming long shutdown, then we will have a really different and really cool new detector that will, however, also be quite challenging to then have the local reconstruction working in an efficient and fast way and so on. So that's a besides the sort of construction of the hardware itself, it's also a very challenging thing to actually also make use of all this information that we will get. So, but then we will have this much more this much higher granularity. We will actually then also see we will be able to do some kind of tracking in the calorimeter of individual shower starting events, and then we will also have some sort of tracks of the secondary particles of the showers, and if we are sort of very, very clever using that information, then the hope is that we will actually then be a very, very strong calorimeter also. The calorimeter resolution, then I was mentioning, in principle goes down with the energy, but then there are different terms, and there's also usually some constant term which then sort of stops the improvement at some plateau. One usually has this sort of parameterization of the relative energy resolution. There's this stochastic term, the noise term, and the constant term. With the constant term, one can actually run into trouble, and also, for example, the intercalibration of integral detector parts is not perfectly done. In general, there will be some sort of plateau that one cannot really overcome completely, and then the tracking is more starting from very good relative energy resolution, and then at some point goes linearly. So there's some overlap, and if one wants to combine the material and take the information for the reconstruction of the particles, and one has to see what is the best sub-detector for different energy regimes and for different particles. And for charged hadrons, this is mostly the tracker, particularly at low momenta, and then only at very high momenta, then the energy resolution of the calorimeters might take over. Then we have the electromagnetic calorimeter, which covers the electrons and photons, and the neutral hadrons, they solely rely on the H-type, which has relatively not so good energy resolution. However, there is also a relatively small fraction of the shower, so we cover most of it also in the particle flow algorithm, then with quite a good precision. Okay. So that was first sort of general discussion of tracks and E-cut and H-cut. Now we talk a bit more about these aspects of for example, the pulse shapes also.
We keep running faster and faster. I don't know what we're after, yeah. We keep up with disaster. I'm thinking that they're after me. Running like faster and faster. Running like faster and faster.
Means no CP violation in both cases. 90 or minus 90 would mean maximum CP violation. What this experiment could do, but mind you, with something like hundreds electron neutrino events in T2K, even less than that, they could exclude at 3% confidence level that delta C, the CP angle, that delta CP was in here. These are excluded at the 2 sigma level, and the most optimal value they found in the fit with the neutrinos and antineutrino oscillation they saw is that it's around minus 90 for the almost close to maximum. That was very exciting because if this CP violating angle is close to maximum, it could well mean leading to a good explanation why there is matter in the universe as we see it, and we don't see antimatter in our core. So that has been done through what they call lepton genesis, which created a baryon asymmetry. Good. Just to finish this part, is we have all you can look of all the experiments, what all they have measured in all these cases. They have for theta 1, 2, theta 2, 3, theta 1, 3. CP violation and so far. This is already a few years old now. It's an update, but it basically gives that you can get values for these parameters out, which you try to measure. Now this is dry, you don't need to see what that means, so give me some idea of how it interprets. It would mean the following thing. Say that the electron neutrinos are the dark blue, the mu neutrinos light blue, and the tau neutrinos red. It would mean that the composition of these 1, 2, and 3 mass states is like this. In this case, the new one is mostly electron neutrino with a little bit of equal partition of mu and tau neutrinos. The new 2 state would be like equally partition of the 3 flavors, and in the third state you would have mostly mu neutrino, tau neutrino, and a little bit electron neutrino. So that is how you interpret these numbers. Now talking a bit more on the neutrino properties. Mass, for example, the smallness of the neutrino mass is amazing. It's a million times smaller than the lightest particle which we have, which is the electron. We don't know the absolute values. We could have a normal hierarchy that mu 1 is the smallest and mu 3 the heaviest, or the inverted hierarchy, mu 3 is the smallest and the other 2 are the heaviest, and they are very close to each other. Now note that the very lightest neutrino could still have mass 0, because we only know mass differences, and there could be always still one neutrino which has mass 0, one mass stable neutrino mass 0. That keep in mind. We have several ways of looking for trying to find the mass, and the most model independent, I would say, which you can have is looking at beta decays, like how the neutrinos were discovered in the first place, or at least postulated by Pauli in 1930. And that is a neutrino beta decay, which means an electron or a neutron. A neutron goes to a proton plus an electron and an antineutrino, and you measure the endpoints of the electron which you see, which can tell you that the kinematics allows for this neutrino to have some mass, or the neutrino will be 0 mass. So you have to look at the very endpoint of this distribution of the beta electron spectrum. The Catherine experiment is the one which is looking for that, and that uses the endpoint of a tritium decay.
Paper in 2016, which was published in PRL, and you can see that in the lambda B decays, actually they have found a state which they call as a pentaquark state, and it has the charm quarks as its content. It has a C quark and a C bar quark, which we always call as a closed charm states. Why closed? Because we don't have any vacant charm number. Because C has a charm number 1, C bar has charm number -1. Therefore, if you add the two, because these are the additive quantum numbers, then at the end of the day, you have a 0 charm number. So they have found this state like in the GF psi P. GF psi is basically CC bar and proton, up and down. So it means if you have a state that has quark contents like C, C bar, U, and D, you can just rearrange those quarks by using the Zweig color allowed rules. Then you can just make a state for that, which is known as a pentaquark state. So they said that the GF psi P comes from the decays of the pentaquark state. That is a resonance state. That's why you can see these resonance peaks. And then there were a lot of papers written prior to the discovery of this state and after the discovery of this state. For example, this is one of the interpretation of the pentaquark state, which I told you about, just like the tetraquark state, which is a QCD bound state, in which you have four quarks and one anti-quark, right? So these are the QCD bound states, like the tetraquark state. They are tightly bound states. I mean, they are bound by the gluon interaction. And then there is a molecular state. What is molecular state means? You have a baryon and you have a meson. Three quarks rearrange themselves to make a baryon, and the quark and anti-quark arrange themselves to make a meson, and they interact with the van der Waals forces like in the tetraquark molecular picture. That's why this is known as a molecular picture. So I just talked about these two. I'm just skipping these kinematical effects because these two approaches we have explained in detail yesterday. So, as I told you that over interest was in the diquark and diquark approach, so we followed exactly that approach to predict the masses of some more pentaquark states back in 2018 and 19. The idea was following. We have considered one quark-quark shell, which is known as a diquark, and I told you that if you combine two color triplet quarks, then you get 3 bar and 6. And 3 bar was attractive and 6 was repulsive potential. Exactly, you have a 3 bar from here. So if you combine 3 bar and 3, then from the SU3 representation, from the irreducible representation, you get 3 and 6 bar. Now if you combine that 3, which is this color 3, with this 3 bar, you have 3 bar, which is equal to 1 plus 8. So perfectly fine, you can get a color signal from it, a color neutral laser. This is how we have formulated the pentaquark state. The idea was this one, that these two diquarks are in the relative angular momentum 0 state. I mean, they are in the ground state. And this anti-charm quark state, which we have shown as outside this shell, it is in L is equal to 1 state compared to that. So as a whole, we can have a pentaquark state as L is equal to 0, which is a ground state, or it is L is equal to 1, which is just like the vector states we have in the tetraquark states. Once again, the effective Hamiltonian was same. This is the effective Hamiltonian that contains the masses of this diquark, and a charm quark. Diquarks and charm quark is separate. This is the coupling of the quark inside the diquark. I told you that we have ignored all those coupling that lies outside this diquark shell. We have considered the coupling spin-spin interactions between the quarks inside the diquark. And this is a spin orbital, and this is the orbital angular momentum term, and there is another tensor term which do not contribute for L is equal to the L is equal to 0 state, but that will contribute for L is equal to 1 state. For L is equal to 0, this term is 0, this is 0, and the tensor term which I tell you in the next slide, that will contribute. So actually, this was something that we have predicted in our first paper of 2016, and you can see that 4380 is observed state, 4450 is observed state. By the way, we haven't predicted these two states. We have used these two states to predict the other states, because I told you that in this model we have some free parameters, the free parameters like kappa, A, B. So if we know two states, at least, which are L is equal to 0, we can fix this and the mass of the dipole. This is perfectly fine. So by fixing the mass from the known state, we have predicted the new states, and we hope that in future run we will observe some of these states. But that was an old story. After that time, the LHCb refined their analysis, and they said that okay, instead of 4450, they have now resolved to two states, because previously they have two states, 4380 and 4450. But the 4450 state is further resolved to two states, which is 4440 and 4457. So instead of two pentaquark states, now we have three pentaquark states. So what we have done is, we have slightly modified our model, because I told you that this is not necessary that you follow one approach. This is the latest approach that is more acceptable now in this spin-spin interaction. It is exactly, just remember this slide. We have two diquarks and a C bar. outside. Slightly change this one to this one. We have a diquark in which one is a charm quark, other is a light quark, and C bar. There is no problem. This 3 bar will give you 3. And this light diquark is an external shell. Once again, instead of having C bar in the external shell, now we have a diquark in the external shell of this triquark. So this is kind of a triquark diquark picture. And this diquark is in L is equal to 1 compared to this whole shell in which we have a diquark and an diquark. It's a very simple approach. Once again, the Hamiltonian is exactly the same. Now the idea, as I told you, that for the Hamiltonian you need a state, and for the state you need the quantum number, right? So what are the quantum numbers that are necessary? Every undergraduate student can write a quantum number. You can see that, okay, there are the quantum numbers of this heavy diquark. Why this is heavy diquark? This red color is charm, and charm is heavy. You need the quantum number of this triquark, because how the spin of a heavy diquark is combined to the spin half, because now it is spin 0. If it is added to spin half, you have a spin half. If it is spin 1, if we add spin half to it, there are possibilities that we have a spin half and 3 half. So that's why I said that then there is a triquark, and then there is a LT, which is the angular momentum of this triquark, which is always equal to 0 in our approach. And then we have the spin of a light diquark, angular momentum of a light diquark, which is equal to 1 compared to this one, and the total spin of this pentaquark state. That's all. These are the maximal quantum numbers that you need, or the minimal quantum number, whatever you say, in order to perform any calculation regarding this pentaquark state. So I don't want to go into the detail of the pentaquark calculation. It's a very long paper that is around 50 pages. And here are the outcome of those papers. These are the states which we have used to fix the parameters, and we found that there is a state which is lighter than these states that has a mass of 3.8 GeV. Just remember these are in the MeV, so you can just say the 3.8 GeV to a first significant figure, to a first decimal place. And then you can see these green masses. They lies closer to the mass that was observed at the LHC. So we hope that in the future, when statistics will improve, data will improve, perhaps we can find some more pentaquark states. And the states which we have circled, which are circled over here, they are the predictions of the older paper. So that's why we have written the old prediction and the new prediction. And you can see that some of them are very far. Why they are very far? Naturally they have to be far because the approaches change, masses are resolved, parameters become more refined. Therefore, these are the updated masses that we have used.
we keep running faster and faster. I don't know where we're